see,
Yes,
just to make
yes.
sure you can see the slides? Okay, brilliant.
Yeah.
Okay, so as I was mentioning, I want to really do an introduction kind of to computer vision, a little bit about how these models are built, and the structure of how the development has kind of occurred over the recent years. Plus, I want to go into a little bit about how you build or how you do performance testing, and how do you actually measure these type of models? Because I think there's a lot of discussions you'll probably see on medium.com, on towards data science, and even if you're reading the academic journals on this, and if you're not really sure on what these measurements means and these metrics, it probably can be a little bit confusing. And always having the fundamentals is probably useful for you guys. If we get time, then I'll transfer over to looking at machine learning on AWS, and then looking at this use case. If we don't have time today for the use case, it is, which is effectively object detection, building object detection models. There is a GitHub repository, which you can go and navigate to. On there, it's got all the code. It's got a very, very long blog post explaining step by step how things are built and kind of developed, and it will follow along from the discussion we have today. So kind of let's kick things off with a little bit of what computer vision and a bit of the background on this one. So ultimately, you might have seen this or this kind of image many, many times, is the goal of computer vision is to perform different types of computer-driven image recognition tasks, whether that be object detection or object classification, or even segmentation, so i.e. detecting different regions within an image, or for different color patterns and different line patterns. Those are the basic goals of computer vision. However, it is not that simple to do, because computers do not understand images, and they don't understand the pixels effectively in those images. So we need to find some computational way to achieve this task. Guys probably have some familiarity with machine learning. I'm not sure what the level is you guys are at, so I'm going to go a little bit of intro. Assume that you understand the basic concepts of machine learning, but I'll break it down in the form for computer vision. So before we go into computer vision, just a quick intro: artificial neural networks. So everyone's heard of neural networks most likely on this call. If you haven't, no problem. I'm going to take you a very quick guide through this one. So the basic constructs for a computer vision algorithm or model in the most recent years are based on the fundamentals of a neural network. A neural network comprises of, the first thing here is called a neuron, and nothing that complicated here, but we'll see how it gets complicated. So neuron effectively is just a simple function, which, and when I say function, don't get confused on that either, which is effectively takes a bunch of inputs, it adds them all up, it applies some function to that. So that function could be just adding them up and providing the output, or it could be doing some transformation. And as part of that transformation of that input to output, we start to build our model effectively. We start to build information, store information within each of these neurons. Now, one neuron on its own doesn't really do much. So if we had an input x1 to x3 and each one represented one figure, so numerical 1, the output would be numerical 3. So that would be a linear addition of all of those numbers. But that doesn't really give us any kind of benefit by doing that. However, if you were to take all of each individual neuron and add them together in a network, what we start to get is this thing called a neural network. So we have a bunch of inputs, we have a bunch of kind of hidden layers, those orange layers, and we have an output. And in each one of those neurons and each one of those circles, once it hits the hidden layer or the output layer, we start to apply different functions to it. And those different functions typically perform transformations of the inputs to outputs. And those transformations, if anyone has ever done machine learning, kind of the basics of machine learning, so from doing linear or logistic regression, we're effectively, those weights become our coefficients in the network. And the more coefficients we have, the more complex the network has. So the more neurons, the more complex. And what you're seeing here is that layer L2. That is effectively a hidden layer. you don't see it when you're computing it. You only see the input and output. But the more hidden layers you have, the more complicated the network gets. And the more layers you have, the more information can be stored. So typically what you would do, you end up having your bunch of inputs, you have an output, and in the middle, your aim here is to train the network to effectively find the lowest cost, and we're going to talk about that in a second, to predict from the inputs to the outputs. So what does that actually mean? So again, very much similar to traditional machine learning. If you've ever done anything like linear regression or logistic regression, you have two additional components. So you have your data and you have your Y targets. So whether it's being a regression, so it's numerical values, or it's labels for a classification task, you need to be able to minimize the error between your inputs and outputs, assuming there is some correlation between the inputs and outputs. So say you have a number of rooms and house prices, what you would end up trying to do is show that if you predict accurately enough with the, finding your line of best fit or your line of the equation, the amount of loss, so the amount of error between the inputs and outputs is reduced. And to do that in the neural network world, we're doing the same thing. We effectively have a cost function where we're trying to minimize the amount of error, and we do that by doing this thing called a forward propagation, so forward pass. So we compute all of the weights on each of the neurons, and on the end we have an output, and that output then we can use to determine how much error there is between the input and output. And then using an optimizer, which is something similar to, you may have come across gradient descent, but effectively an optimizer is a way to determine how much to adjust the weights of each of those neurons or in the case of gradient descent, how much to adjust the weights of the coefficient, the line, the angle of the curve, and the height of the curve, or the height of the line, the angle of the line, depending on the type of model you're building. And using those optimizers, we try and reduce the amount of loss or the amount of error that we have within our network. And that process is called the backwards propagation. So the reason why I want you to be familiar with these things is because when people talk about, and you probably, I might be preaching to the church here, but it's, in many cases, there are lots of different parameters that people talk about in neural networks and in computer vision. And sometimes people use them without really understanding the underlying kind of purpose and kind of theory behind them. And it's always useful to have that in the back of your head when adjusting or when building these models or when even playing with it. So with that being said, let's move a little bit along, because these fundamental principles of machine learning, of neural networks, of optimizers, cost functions, and weights and coefficients are translated all the way through to CNNs, which are convolutional neural networks. So the basic constructs of a computer vision algorithm in most recent years, when we're looking at the neural network approach to performing computer vision, is to be using these convolutional layers to be able to scan across an image and break it down into subcomponents or subparts or subregions, and then using this scanning, and we're going to talk about that in a minute, and kind of passing over the image, we build up a deeper representation of an image. Now, each image contains different colors, different sizes, different orientations, and we use this scanning mechanism to do that. And we're going to see what that actually means. But effectively, what we learned in the past is that using something like a traditional linear regression or logistic regression or some form of classifier to be able to determine regions in an image wasn't that effective. And there was too much information to encode. And also, there is quite a lot of diversity in images. So traditional machine learning approaches were not very effective in being able to determine patterns or find patterns within these images. So we devised a mechanism. But I just want to say, if anyone has ever come across this image before, please say in the comments. I will give you kudos afterwards for this one. But effectively, when we talk about an image, an image is a representation of a matrix of numbers, okay? And those numbers could be generated from the intensity of the pixels, the kind of the complexity of those numbers could be constructed from the different channels in the pixels. So it could be, the red, green, and blue. It could be the orientation. But effectively, what we need to remember is that what we have when we have an image, what the computer sees is just a matrix representation of that image. So what we want to be able to do is over time, get enough images, get enough matrices, and see if we can find patterns in the way those matrices form to be able to determine if we can predict certain things about it or identify certain objects within that image. So as I mentioned earlier, so I'm going to go through now is just some of the layers used within a CNN architecture. Now, when I say architecture, don't get confused. It's not multiple services. What I showed you before with the inputs, the layer 1 and output, that is a simple architecture. It means it's got one hidden layer and it's got an input and output. However, when we're trying to build computer vision models or any neural network, in fact, that is not a toy in some sense, we need to have architectures which are more complicated. We may have multiple layers. We may have more dense layers in the sense of more neurons within each layer. So when I say architecture here, all it means is the connection of layers put together. Okay, so from your inputs and outputs. So one of the layers that we need in a convolutional neural network is obviously the convolutional layer. And what we're going to see here is two components. One is your image, your input, and the second is the kernel. And the kernel is nothing more than effectively a smaller matrix, typically smaller than the image size itself, otherwise it wouldn't make sense. And those kernels effectively move across the matrix of numbers. So in this case, the inputs, that representation I showed you just on the previous slide of the representation of pixel values, and provide a way to break down the image into regions which are of the size of the kernel. And what does that actually look like? Well, if we started with an initial image of height times width, and the kernel is, let's say, 5 times 5, and the image was, let's say, 100 times 100, we would see that the kernel moves from the first pixel and scans and scans and scans, keeps moving all the way through until it reaches the very last pixel on that top line. But by the time it's done that, it's now taken a series of sub matrices which represent that first region within the image. Now, why would you do that? Well, what you're actually starting to do by doing this striding and kind of pacing over the image is you're starting to build a deeper representation of the relationship between values. In this case, it's the input values from those pixel values, to be able to determine a little bit more information, compress more information into our network. And remember, every time you do that, each one of those represents a neuron with a network. So each neuron now is starting to be encoded with information about a specific region within that image. Now, we don't need to go into too much depth here, but one thing is probably important to understand is that the size of the kernel and how much information can be kind of encoded every time we do a pass over that image is highly related. So the bigger the kernel, the more information you can encode, but potentially you add a lot of noise. The smaller the kernel, the less information, but potentially you're isolating certain aspects of that image or of that region, which is going to be useful. Typically, we work from kernels from 3 times 3 to 5 times 5, maybe up to 16 times. It all depends on the type of task being performed and the speed at which you wish to be doing the training and the inferencing. We'll talk about that in a bit. But effectively, what we've done now, we've taken that image, the input, and we've now broken it down into smaller representations. And just another note, it doesn't necessarily, and we'll see this in a bit, the convolutional layer does not necessarily have to be used on the input layer. It can be used within the hidden layers as well. And that's where the complexity in convolutional neural networks start to emerge, is how you build these layers up and how you use them. So one of the things that you're going to start to see is that every time you do a convolution across your image or across your layer, what you're starting to do, or you add a convolution in, should I say, you're starting to encode more and more information. And you can see it can grow very, very quickly. And each piece of this, each row and column, so each unit within this matrix encodes a certain amount of information. However, if you start to build very large or multiple layers within a network, you start to build a very high number of parameters. You start to have a network which has lots of neurons and lots of parameters, because remember, for each neuron, there's going to be a set of weights and coefficients that are associated with it. Now, if anyone ever done partial differentiation and tried to do a long set of differentiables across a network, or in general in calculus, you can see it gets very complicated very quickly. So what we try to do is we try to reduce the number of parameters in our network to a manageable size, because remember, the more parameters you have, when you go to train and update these parameters, it's going to take a longer amount of time. So one of the things that's been introduced is the pooling layer. And pooling layer is effectively just a mechanism to encode more information and reduce the number of of parameters down in your network. There's different types of pooling layers, and there's different sizes that you would use. It works in the same way as a convolution in terms of it strides across the image. It slides across the image at a certain rate, and the size of the pooling layer and the type of pooling layer being used will have a different type of output. Just in front of you here, what we have is the max pooling layer, where you can see the figures, the 1, 0, 4, and 6, which is in orange. What this pooling layer does, it says, give me the max value in that 2x2 region, and it does 6. And the same thing for the orange, for the green, same thing for the blue, and the same thing for the gray. Different types of pooling layers have different kind of outputs, but effectively it allows us to reduce the complexity that have occurred because of the convolution kind of approach. Okay, so the next thing we want to get to is, hey, we've taken all of those inputs, we've done all of the convolutions, and maybe we've applied some other layers, which we'll talk about in a bit. What we need to do is get an output out of this. We need to bring back all of those inputs, which would be all the different neurons and how their inputs are, and bring them to a fully connected layer, which is our output layer. Now, depending on the type of task that you would wish to do, you need different types of output layers. And we're going to talk about why that is and how that actually kind of occurs in a bit. But effectively, the output layer allows you to, in practical terms, allows you to do classification, for instance, depending on the type of output layer you use. It could allow you to do a regression-based approach. So it's effectively our way of bringing all of the hidden inputs, potentially maybe not hidden, but hidden inputs all together and find some final output. In the case of classification, we'll look in a second, you use a specific set of activation functions within those neurons on the output layer to allow us to do some form of classification prediction using cross-entropy, but we'll talk about that in a bit. Don't worry about that. So we've gone from inputs, convolutions, poolings, and the final fully connected layer. But inside each one of those neurons, there's something happening. There's something going on to those inputs to outputs. We're not just doing input added output, because that wouldn't make any sense. We would end up having no learning. We would end up not actually providing any kind of ability to encode information. All we would end up doing is having a linear input to output, which doesn't provide any benefit to us. So what we need to do is have some form of function that sits within these different neurons. Now, there is a lot of work, a lot of academic research into this space, and I'm not going to go into the depths of it here, but effectively there are a collection of different activation functions which can be used, which provide nonlinear transformations to your inputs to outputs. And why do we want to do that? Well, the most important thing when we're doing machine learning is being able to improve our correlation, let's say, between the inputs and outputs. And to do that, we need to be able to not improve the correlations, we need to improve the fitness of the model, so the goodness of fit of our model, to be able to reduce the amount of error between the input and the output, assuming there is some correlation between the two. I think everyone never really talks about that, but sometimes doesn't matter how much you try and build models, sometimes the data does not work for machine learning purposes. Just to always think about that before you go into these problems. But refocusing on this, we need some way to transform our inputs to outputs, and we need to do it in a nonlinear fashion. And why is it nonlinear fashion? Well, that way we can confine it within a specific set or a specific range. Like you can see here in this region, sigmoid function, which we'll talk about in a bit, allows us to confine it between 0 and 1, where it reaches the asymptotes. And by doing so, it allows us also to do continuous kind of differentiation across that line, or integration across that line. And the angle of the line, so the where it crosses the x-axis and maxes out at the y-axis, provides us a way to interpret those weights within a certain scale, so within a certain region. And there are problems with each of these different activation functions, but I mean, the best thing here you can take away from is that different activation functions provide different desirable results. So ultimately, the aim here is to use these activation functions to squish effectively our inputs into a certain range, and to allow us to reduce the amount of error within using a cost function, which we'll talk about, by using some form of optimization, whether it be a derivative of a gradient descent. So if anyone's ever played with that, gradient descent allows you to find the derivatives of a line. And then by using that, the derivatives of a line, we can reduce the amount of cost by moving up or down the direction of that gradient. And those sigmoid functions and ReLU functions and other types of functions, tanh, provide you a mechanism to find the gradients of the line, which is associated with an error value. So that being said, one of the really kind of useful activation functions beyond these two, the ReLU and the sigmoid, just to note on that one before I move over, actually, there's a whole bunch out there. Please go and have a check the different types of activation functions out there, because you'll see they have different impacts for computer vision models, specifically for object detection. But one of the most important ones that we'll see being used time and time again is SoftMax activation function, which is typically used at the very end of our on our fully connected layer, because it provides you a way to do classification. So if anyone has done logistic regression before and built themselves a cross entropy kind of model, so they understand cross entropy, you'll understand that the SoftMax activation function looks very similar to sigmoid. And effectively what we allow us to do is it allows us to do classification over a decision boundary. And that sounds complicated, but it effectively says, are the inputs probabilistically related to or statistically related to a specific class? And depending on the decision boundary, in most cases in classification, it may be 0.5. So over 50%, we say, yes, it's over that one class. The probability is related to that one class. That's great. We can now assume that the prediction is associated with the class. And say we have multiple classes, then we're starting to build, and effectively in this approach for SoftMax, we build these sparse categorical cross entropy layers, which effectively means, if you've played with machine learning before, the one versus all or one versus rest approach to building a multi-label or multi-class classifier, which means, is this input related to this class and not any of the others? And then it gives you that the probability distribution for all of the different classes, and then you can select using, computationally, you can select using the highest value within your output as which class it associates with. So sounded complicated, but effectively SoftMax allows us to do classification for for binary and multi-class classification problems for neural networks. And specifically, this is used a lot in computer vision for image classification. So, is it a dog, is it a cat? Every time that's doing, at the end of that, under the hood, there is a SoftMax activation function, which provides a probability distribution between the dog and the cat. And depending on which is the highest value, you will take that one and then associate it with a specific class label. So complicated, but very useful to learn. There are different types of activation functions depending on the task. Recently, I was building one with, if anyone's used SVM before, support vectors, you can use those as an activation function at the end. Gets a little bit more complicated and doesn't work very well with large data sets. Please talk to me offline about that and I'll tell you a fun story at some point. So a few other layers before we go into something a little bit different. I'm appreciative of the time as well. We're already at 9:35. I'm going to say we'll probably get through some of the theory on this one and then see where we get to by 10 o'clock, okay? Or 10 o'clock my time, 7 p.m. your time, Seattle. So the next one is the loss and regularization layers. Now, don't need to delve too much into these, but if anyone has done machine learning before, regularization is a technique to stop effectively overfitting by penalizing the coefficients within the network. There are different techniques that are used in computer vision. This is particularly important because we want to, as with any machine learning model, we want to be able to generalize, build a generalizable model, which effectively means it works not only on the data that we are looking at, but data that resides outside our test or training data set. Now, to do that, we need to be able to not have a model which fits perfectly to the data, but we need something that fits pretty good, but also doesn't fit to every single data point like we see on that chart there, you know, with the high variance. It fits pretty much around all use cases, all data points, but if you tried to generalize about that, it would have no use outside the training or test data set. So there's different types of layers that are used within neural networks. These are super important because they play a big role in being able to make these models generalizable. So one of the layers, which is very simply a dropout layer, and all this effectively does, it allows us to just turn off, just think of it like that, turn off certain nodes or certain neurons within the network to stop the inputs and outputs happening. And by doing that, it reduces the ability for the model to overfit. Because if you think about how the neural network works, it's a construct of different layers, and each layer encodes more information. If you encode so much information, you effectively create a perfect representation of that data set in your parameters. You end up, when you're trying to use it on a different data set, it's not going to work very well. Mainly because it's encoded or it's been, you know, trained directly on that data. So if you turn off some of the layers for training or turn off some of the neurons, you end up with not the best representation, but good enough. And that's effectively the underlying kind of approach and theory behind dropout layers. Another approach, which is more recently kind of being developed and then used significantly in CNNs, is this batch normalization. Gets a little bit hairy, the math in this one. So I put in the link how it's used from the paper that was published on this one. But effectively it allows you to normalize multiple weights and accelerate their convergence inside each of the batches. Because when we do machine learning, or when we do training in a deep neural network in a neural network fashion, we never give all the data in one go. We do it in batches effectively because the data sets are too large. But that means what we end up doing is potentially we could create parameters which are more likely to be tuned to a specific batch rather than the overall data set. So what we end up using is something like batch normalization, which allows us to reduce the internal covariance kind of shift inside each of these batches. Not too much worry about this one, but just to note, you'll probably see these layers within these neural network architectures I'll show in a bit. So finally, we've gone through what neural networks are, specifically for convolutional neural networks for computer vision. So we started at the image, we did some convolutions, we did some pooling, we did some more pooling and convolutions and maybe some dropouts. And at the end, we had this fully connected layer, and we have some SoftMax function at the end. And at the very end, we can predict what type of image or what type of object or what classification that image represents for our model. Pretty good stuff, pretty complicated. And I know what I've gone through is probably a lot of work and skims over the surface, but I wanted to give you a handle on those different components, because when you see these images, of neural networks, of layers within that, it needs to make sense to you to understand how you use it. And I'm a strong believer on, if you understand the fundamentals of something, you'll get far, you'll understand further a lot more how to develop it in your own way and how to use it intuitively rather than just using it off the shelf. It's always much better to understand fundamentals. So a few more things. So one thing I haven't talked about here is hyperparameters. And they could be coming from traditional machine learning, like learning rates and offsets for your kind of initializing weights for your parameters. So remember, every time you do training, if you've ever just done very simple linear regression, you need to initialize the weights of those coefficients, the mx plus b, the m and the b. You have to somehow initialize the bias, and you have to somehow initialize your coefficients. So in neural networks, that can be actually quite challenging, because say you have 100 million parameters, where do you start the initialization of these parameters? So different hyperparameters are used to do initialization, as well as learning rates and a variety of different functions or different parameters within the models. Playing with hyperparameters, it will not only help accuracy, but will help reduce the amount of training time required to achieve a reasonable result. It's also important because you'll notice in most of the journals and papers published on this, hyperparameters are always stated, because if you want to reproduce a set of results that you'll see from like a performance output, you'll need to use the same hyperparameters. So it does make a difference. One of the things I will say is AWS or Amazon SageMaker provides you with a hyperparameter tuning kind of mechanism. It's awesome. I mean, it's really great. You can take your model, first train it with some random hyperparameters, see if there's actually any use of using machine learning on that data set. If there are, then you can use the hyperparameter tuning solution to improve those parameters, rather than doing a naive or a grid-based search to improve them. As I say, deeper architectures plus hyperparameters improve the training speed, or it could decrease it. But there is always the benefit of, you have more compute power, specifically with GPUs, you can start to reduce the training time and increase your inferencing time as well. So a little bit more. So one thing is about building the models. The other thing is about understanding your data and being able to build a data set which is going to help you achieve your computer vision or machine learning tasks. In fact, more generally machine learning. So we need good data sets. We need clean data sets, but we also need, for computer vision, data sets which represent a diverse selection of kind of orientations, let's say, of our image, or different representations of an image. Now, it's no good if we have so we say we're doing a dog and cat classifier, as everyone wants to always build for some reason. There's no good if you have images where the dog is in the same area of the image, in the same region, in the same orientation, without any skewing from different angles. That's not going to do very well. So if you take that model, or if you take your architecture and train it on that data set, great. It will be able to predict the same type of thing. The dog sitting right in the middle of the image, without any twisting or rotations or inversions. So what you need to do is certain things like data augmentation, where you do transformations of the image in different ways to be able to build a more robust data set. Now, people always talk about, and I have a strong feeling about this, people always talk about the models that they're using, whether they're using the latest state-of-the-art YOLO model or whatever it may be. But no one ever talks about the amount of work that goes into building your data set to be able to even use those models. There's no point taking the state of the art if you have 100 images. And we see this a lot in recent years, is that you have very small data sets and people build models and achieve 99.5% accuracy. And yes, you might achieve, in theory, 99.5% accuracy, but what does that figure really represent? How usable is that model outside of that toy data set that you've used? So you need to think a lot about the data. And one way you can improve on that as well is using reference data sets, where models have previously been trained on a larger data set, and now you take that pre-trained model and apply your smaller data set to it. Aha, what does that look like? Well, that's transfer learning. So at the bottom of the slide, you can see there's a bunch of data sets, MINTS, CFAR, ImageNet, and I haven't added on there COCO, but effectively transfer learning is a way of taking a pre-trained model. And the reason why I'm telling you this, because most of the stuff we do in Amazon provides you with a pre-trained model, and you can do just transfer learning on top of it. So it's effectively, hey, we've got a very large data set, maybe billions and billions of images, or we have loads of annotations on our data set, and we want to use that we want to train a model on it, and someone's probably previously gone and trained a model, like Amazon's trained some, Google, Microsoft, they all have pre-trained models. Potentially academic research departments have their own models. And then we will take the model and apply our data set to it, do a little bit of manipulation on the layers within our data, maybe change the output layer or maybe change the input layer, and then we will train it with our new task. So there's three different types. Typically, you would say three broad ways of looking, categorizing transfer learning. Forward transfer, so train it on one task and then train it on a new one. So multitask is train it on many tasks and then transfer it to a new one. So a task, remember, may be, a classification of dog and cat, and then a classification of flowers and trees. So, different types of tasks, and then train it on a new one. So it has a more generalized view. Or you can have multitask meta learning, which is a little bit complicated, but it's used a lot in things like autonomous vehicles, where you build a data set or a model which understands the meta approach to a task. So understands, outlines potentially, or understands some meta kind of data around a specific task, but not necessarily the task itself. So it's used a lot in robotics. I'm going to give you these slides, and I know we've got a little bit of time, not that much left, 13 minutes so far, but there's some more details on transfer learning and in practice. These are kind of the different pathways that you can take from inductive to transductive learning. They effectively map to the discussion I just had regarding multi-learning or kind of domain adaptation or task to task. One of the things I said with transfer learning, it's all about taking that pre-trained model and making very few changes to the model to be able to use it in your domain or in your task. Making too many changes will effectively decrease the capability of the model. One of the things you have to be aware of, though, and this is an active area of research, so if anyone is thinking about pursuing a PhD or master's in computer vision or in machine learning, negative transfer is a great area which needs a lot of work still. It's taking the concept of transfer learning and understanding the negative impacts that happens to the models when you perform transfer learning. So that may be, training on one domain, which is very specific, like handwriting data set, and then trying to train it on a different domain, which may be detecting images of cars, and finding that the actual performance of the model is far less than just having a non-pre-trained model within your kind of architecture. So great area to develop if you're interested in pursuing, further studies in this area. So I've got about 10 minutes, 12 minutes left. I want to just quickly cover one last area, and then we'll see where we're at, is performance of these models. So people talk a lot about performance. Hey, we have 55% accuracy, 75% accuracy, but what does that actually mean in computer vision, and how do we use it to compare models? Probably very useful for you, because most of the time, say you're using SageMaker or you're using your own data science kind of notebook environment, Jupyter or Zeppelin or whatever, maybe even just writing it in C if you're that way inclined. But you need to be able to find a way to compare different models for different types of tasks. Now, there's probably a lot of noise everyone hears all the time: precision recall, area under the curve, ROC, all these different metrics, kind of acronyms. What do they actually mean and how do we use them? Well, there are different types of metrics being used for different types of tasks. Now, the fundamental basics for classification, we're going to stick with classification for the second, and we're going to look at two types. One is for image classification, one is for object recognition. Remember, there are different types of tasks within computer vision, but they fundamentally perform the same thing using similar architectures that we've just discussed. So precision recall, kind of pretty much your basic mechanism or metrics for measuring how well a classification model was performing. Your precision is the measure of accuracy in your predictions, which is the true positives divided by the true positives plus false positives. So just think of it, how many percentage of your predictions are correct. Whereas recall is how good do you find all of those positive kind of predictions. So it effectively true positive divided by true positive plus false negative. But we're looking at, for different types of tasks, the ratio or the values of precision recall may change, but that may be okay. Sometimes you might have a low precision, but a very high recall, which would be specifically used in different domains. So fraud detection, for instance, when you have very imbalanced class data sets, you're likely to have a very low precision, but you'll probably have a high precision, but you want to achieve your desirable result to have a high recall, because you want to be able to find all of those positive fraud cases out of the very big data set of potentially maybe only 1% or 0.01% have the fraud cases, so it's imbalanced. So depending on the nature of the task, you want to be able to use precision recall to your to your aid. Now, just being said, this is the fundamental approach to doing image classification for any classification model outside of just images as well. But effectively, it's we look at the precision recall score, and potentially in papers you'll see one thing that says the F1 score. That's nothing more than a calculation between the precision and recall. Sometimes they call it the harmonic mean. So just to take that into account, those figures are used. So one of the areas which is potentially more useful for you guys outside of image classification, but for object detection, is this thing called the intersection over union. Now, think of this as when you have an object detection training or testing cycle. Effectively, when you're training, what you're doing is you have given the alongside the image, it has metadata for each image, and each metadata contains the annotations, which are effectively the bounding boxes. In this case, in this image on the slide, that ground truth, the bounding boxes which represent where the object sits within that image. And then the area over intersect is how well the model builds its bounding box over the ground truth bounding box. So effectively, if you think about putting one hand over the top of the other, if the overlap is full, if it's 100%, then the IOU is 1. And going from 1, it would go all the way down to 0 if there was no overlap between the predicted bounding box and the ground truth bounding box. And that is one of the fundamental components, which we'll see how it builds up to measuring performance of these models. So if we have a perfect model, we'd be able to predict bounding boxes on a prediction exactly the same as the ground truth bounding box. However, what we try and do is we try and look, because remember, we're not just looking at one image, we're looking at thousands and thousands, potentially millions of images when we're building and evaluating our models. So we need some mechanism to combine both the precision and recall and the area, the intersect over union metrics that we just talked about. So it looks complicated, it's not. Effectively, all we're doing is we take the precision and recall curves that we've talked about before, with how well it predicts and how well it doesn't predict, and we combine that using the IOU. And by doing so, we get the ability to determine what is the average. This is the metric we'll see used a lot within object detection, average precision of this model. So what is the precision for the top K class or top K predictions? Typically, we would set like a boundary on top of this as well. So your average precision has to have an overlap of 50% or 75% or even higher, 90%. What are the number, or we don't want to talk about the raw number, but what is the normalized number of score related to those different levels of precision? And to do that, I'm going to give you these slides and you can look at it at your own time as well. It's very simple, but effectively we do our predictions, then we rank our predictions by the confidence of our model. So without going into too much theory, whenever you'd make a prediction, the model also has a confidence score. So if anyone's done confidence intervals here, confidence score tells us what's the likelihood that that model or that prediction is falling within that specific range or in that probability distribution, depending on the confidence interval. So we, without diverging too much, we rank our predictions by this confidence score. And then we start to build the precision and recall levels. So, is the correct, did the model predict it correctly? Yes, it did. Great. So the precision's 1. What was the recall? Well, it's only 0.2 because there's a calculation underneath that. Where are we calculating from? So we build up our model. We build up our table of predictions, and this is how we build the average precision matrix or table. And then we do it for X number of kind of data points. Maybe we do it 100, 1,000, 1,000,000, depending what you want. And then your confidence score is based on a value which is predetermined. Most people use 0.5. Above 0.5, then you end up with the class being deemed correct. And then you start to see what happens. The precision goes down over time because the confidence is going down, but your recall goes up and down, depending on how many were correct, even though the confidence is going down. So, true, on row 1 and 2, you see the recall goes up, and then it goes up, or then it stays similar because it got some false. Then it went up again, and then it goes down and goes up. So we start to see this kind of shift between the precision and recall. And effectively what we end up with this zigzaggy curve or line. And what we end up doing is the average precision is simply the area underneath that curve. If anyone knows integrals, if you integrate the area under the curve, you get a value, and that value is typically what's being used for average precision. Now, as I said, for any of the mathematicians out there, you typically do a little bit of, you build a function which represents that line rather than doing integrals underneath that kind of staggered line. You smooth it out slightly. But effectively, that is as simple as it is for building your average precision metric. And that is used significantly across many of the object detection models for comparison. So now you have a little bit of more insight into how we measure and compare different models. So when you see AP IOU.5, that effectively means once do all the inferencing and only look at those that have a 0.5 area intersection over union or more, or 0.75 or 0.100, for instance, or it depends on what you're using, so what metrics. But COCO uses the terminology mean average precision, but don't get confused, it's the same as average precision. And those are the metrics which are predominantly used to be able to compare your models. So now you learn the types of models and the types of metrics which are used. Now, Bill, I'm aware we're at 10 o'clock. Can we squeeze, if everyone is happy, just another 10 minutes, and I'll just do a little bit of
yes.
Yeah. So
yes,
what
absolutely.
We'll do,
I mean,
okay.
we can, we want to get, also, we have some times for the Q&As. So yeah, please.
Okay, brilliant. So maybe a quick poll, maybe by yourself, but you can elect the right answer. But we can do a little bit more on advancements in computer vision, and I can show you some models which give you a bit of more intuition on how they've developed. Or would you like to see some AWS content and some code, which then you can walk through yourself later on? What would be the general kind of feeling of the audience of the room, virtual room, should I say? I can't see the Zoom, so someone will have to tell me. Oh, maybe I can.
You can see in the chat. I think
let's
folks
have a look.
to type in the chat.
All right, let me have a look.
Yeah, I think it seems like AWS content is more choice.
Yeah, AWS content. Okay, we will switch to AWS content. Not a problem. Let me just minimize this. Okay, so I would have gone through some of the content around, just to kind of give you, you can have the slides, but it's effectively showing the history of how computer vision models have developed and taking those concepts about pooling layers and convolutions to bring them together. So at AWS, we envision, and you might have seen these slides before, maybe not, envision or kind of separate the machine learning world or the machine learning capabilities into 3 different layers or 3 different tiers. At the very bottom tier, you have the ML frameworks and infrastructure. So that's effectively your core compute. So that would be your GPU instances, that would be your large P3DNs, which are the big, very high capacity GPU instances, which allow you to do lots of deep learning at scale. Plus the variety of different frameworks which are available. So effectively, if you are a machine learning or a data scientist which is very comfortable with building your own containers, managing your own services in terms of managing your infrastructure and understanding that world, that is where you can focus. And there's a lot of scope there, from FGPAs to inferencer chips, which allow you to do inferencing at scale at a much lower cost than if you were to just spin up a VM and run that for your model kind of endpoints. However, at the middle layer, which I think is probably useful for 90% of the people out there on this call, is going to be the ML services. So that ranges from things like Amazon SageMaker, and then inside that, things like AWS Ground Truth, and a variety of different services within there. So this is built on the ML frameworks and infrastructure layer kind of environment to do all your data science and machine learning and deep learning needs. So if you're not too familiar with coding or building your own models from scratch, there are IDEs like SageMaker Studio, which provide you the ability to effectively have like a WYSIWYG interface to building your models, to more familiar environments if you're a data scientist or ML practitioner using notebooks like Jupyter Notebooks effectively. But what it allows you to do is not only collaborate, and we'll look at this in a second, but it allows you to, once you're ready, to deploy distributed training jobs onto a larger infrastructure, which then you can use larger data sets, which we'll see in our example as well. And then on top of that, we have the AI services, which are more kind of like fully managed services which provide specific narrow AI tasks. So from text extract, which allows you to do certain forms of OCR, to things like recognition for image recognition, to Amazon Poly for voice to text. So there are different services at that layer, but I always want to focus on, with the developer community, is that kind of ML services layer of SageMaker. So if anyone has actually used SageMaker before, it's effectively the full end-to-end environment, from being able to prepare, build and train and tune your models all the way to deploying it. And there isn't an environment like that out there where you can really do all of the necessary kind of work, from managing and transforming your data set and pre-processing all the way to deploying it in a very simple kind of streamlined fashion. And when I mean deploying it, I mean really putting it as an endpoint, which can be used as inferencing in a production environment. So at each stage, the SageMaker provides different types of capabilities, from doing the collection of data using kind of your own data set, or potentially you may need to enhance that data set with using things like ground truth, which we'll talk about, to all the way to doing managed training jobs where you can start to scale up your local job, which may be training a small data set, and say you're happy with the model, you can scale up to a bigger data set. To, as I said, one-click deployment, which is effectively one line of code where you can say, once you've trained your model and you're happy with it, you can define a model as a deployed endpoint, which then acts like a RESTful endpoint, which you can inference against. And then on top of that, you can start to doing, human reviews, using predictions, detecting drift using out of Amazon Debugger. It's a great environment to do all of your work in. And one of the most important things is it's being fully managed. So you don't have to worry about the underlying EC2 or VM instances which it's running on. That is all fully managed, and you can select the type of ones you're using, and potentially, if that's not powerful enough for you to do your local processing, you can enable auto-scaling, and it supports a variety of different types of SDKs and environments. One of the nice things you'll see in a minute is when you use SageMaker, you can select the Python environment you're using, the frameworks which you may be using, like MXNet or TensorFlow or Keras or PyTorch, and you can really kind of manage your environment in a way which is intuitive and kind of takes the stress away from putting the effort on playing with the environment, playing with all the time your packages. That's all fully managed. So you can concentrate really on building or kind of experimenting in the machine learning world. So one of the neat things around SageMaker is that ability to also collaborate. So one of the challenges you'll find is that if you work in I don't know if anyone works here as data scientists in an in-house data science team for their company, or potentially you're just working on a project with your friends, collaboration is quite difficult. And if anyone's had the nightmare of trying to merge different Jupyter notebooks or any different notebooks, once you've done a commit and you realize there's problems between each other's code, it becomes quite hairy. Whereas SageMaker notebooks provide that collaborative feature to allow you to collaborate between and share notebooks with each other. And as I say, one of the most important things is when you always got to take into consideration cost, is that ability to kind of dial up or spin down instances when you don't need them. And you're not having to worry about the actual underlying infrastructure to do that. It's effectively start service or stop service. So it all takes that heavy lifting. I suppose one of the really awesome things about the kind of infrastructure from AWS is the ability to speed up stock TensorFlow up to around 90% optimized for training jobs. And that happens not only because of the images which are used on these instances, but also because the ability to scale across a distributed set of compute infrastructure. So you end up with a much faster training cycle when trying to build or train your models and evaluate them, which is super important for time, but also super important for costs, because the longer you run jobs for, the more costly it becomes. And I have seen differences between using different infrastructure local and spinning it up on a training job on AWS. It makes a significant amount of difference, especially when you start to do very large scale data science or training jobs using neural networks. So one of the other things I want to just say about is, let me just run through all this, is the pre-built algorithms which are available in SageMaker. Now, if anyone's used sklearn before, you effectively want to import some models, you want to take your data and you want to apply those models to that data to be able to train and fit your data with that model. Now, one of the beautiful things about SageMaker is the ability to take those traditional classification, where it might be XGBoost or some kind of linear learner, and use them in the SageMaker distributed environment. So you can start to use very large data sets to be able to do kind of different types of operations, but within this distributed framework environment inside SageMaker. Those algorithms are also available for different pre-built, as I said, or pre-trained models as well. So you can use neural networks, which have been pre-trained on ImageNet or COCO dataset, and they're all available out the box in SageMaker. There's a really nice feature as well, which is the GluonCV deep learning toolkit for computer vision. So there are, and we're going to look at this in a second, different types of computer vision frameworks out there to kind of packages out there to build your models. GluonCV is available as well, and it provides you state-of-the-art kind of results if you compare it to the latest research papers. I think one of the great things, sorry, with the double type of AWS there, I got too excited, I think, with AWS, is the RCNN model, which is available on the SageMaker marketplace, or it's actually, I think it's part of the core algorithms which can straight out the box. But effectively, it allows you to do object detection, multi-region, multi-object detection, and there's a variety of different models out there as well. But just to say, if we compare the training times on AWS and the kind of inferencing time, it's much faster than I've seen in other kind of infrastructure. So it's a great way of demonstrating how you can do computer vision with pre-trained models and then applying it to your own domain. So one last thing I want to talk about before we shift maybe to maybe another 10 more minutes and we should be done, is talking about marketplace. So hey, you may be a great developer, you may be developing your own models and you think they're really useful, but why not share that with the community? So the marketplace is effectively a way you can share or obtain models that other people, other organizations, teams, collaborations have been using for their research or for their production environment. The marketplace has hundreds of different types of algorithms, not just related to computer vision, but it may be basic classification models or for other types of things. And they're all there. And there is a variety, I think 60 plus, if not now 80 since I last looked, of different computer visions pre-trained for specific types of tasks and domains. So from healthcare to kind of object detection, there's different types of models that are available. Some are free, some come at a cost, but it all depends on what your use case is. But at the same time, it also could be useful to understand what type of tasks can be achieved with computer vision. So I definitely recommend after this chat, after this talk, to go and have a look at AWS's marketplace as well as SageMaker. So Bill, I have a section now on how to use object detection models in SageMaker. This may take around 15 minutes if people are still willing to stay on the call.
I think that probably too long. Also we probably want to save sometimes for the Q&A. Just to get some discussions, questions answered.
Okay.
Maybe for that session, maybe in the future, another session,
Absolutely. And what I'll suggest, I'll just show you now so you can see. So this section here is effectively a quick overview of what you could be looking at is here. So I'll share this link with everyone, but effectively it's a full end-to-end guide on how to use multiple objects from doing object recognition and object detection using Amazon SageMaker. So if I share that link with you guys at the end of the talk, please have a look through the blog post and then go to the code repo, which is next to the blog post, and try it out for yourself if you with the AWS credits which you have available.
That's great. Yeah, I think we probably a lot of folks really like this kind of the more practical and hands-on.
Sure, it's typically with this one you won't need too much context around and kind of skills around machine learning or CNNs to use it, because it's quite intuitive and it uses the pre-built models. But it'll be good for the attendees to understand how to put things together in the context of SageMaker. So yeah, please go and have a look. I'll share that link with you guys.
Right. Okay. Yeah, that's great. With that, okay. So you know, it's a lot of content, and but I do want to make sure we have some times for Q&A.
Sure.
If you have questions, you can type in the chat window. We can go through the questions in the chat window. I think there are already quite a few.
Yeah, let's try and do that. Let me just get back out of this. For some reason, my
by the way, for the videos and this session is recorded and going to be available in the YouTube a few hours after the session is done. And also slides, we're going to share it out after the session. So we're going to send follow-up emails. So you're going to get all of them.
Okay, yes, it is the Doge, Jay said. That was the first open question. Yes, I did obsess about the Doge. And although this is a bit of a diversion on what we're talking about, is I used to come from an academic research. I used to come from a university where the Doge was used heavily in everyone's slides. So I still carry that through with me just for a bit of legacy purposes. So that's why. What's my favorite Slack channel? I don't actually go on Slack channels. I find if I start doing that, all my time will disappear because I have a desire to answer every question that I see. So yes, I don't go on Slack, but I do follow, it's academic. I do follow most of the conference proceedings when they come out. So that's my indulgence of machine learning papers. I try not to read too much of the articles available kind of on like the towards data science too much, because I find myself then not delving into the depth of the details of the paper. So effectively what happens, and that's fine, I mean, depending on where you want to put yourself at, is if you read a lot of the towards data science or the medium.com posts, they're good, they give you that first level understanding, but unless you are willing to go and read the papers afterwards, I feel like sometimes I lose that ability to then interpret what's going on behind the scenes. So don't have a Slack channel. I do like dl.acm.org. If anyone knows what that is, then they're probably academic. Any other questions?
In the chat, I'm not sure if you can see that.
Let me have a look. Oh, let me have a look at the chat.
Yeah.
Where is chat?
There is a
yes,
button.
I see.
Yeah.
I got it. Okay. What would be the ideal learning rate for any machine learning algorithm? Okay. That is it really depends on the type of model, the type of data set you have. Typically, you would start at at the micro, so 0.001, and then increase or decrease around there. So remember, in many of the good optimizers which are used for neural networks, Adam or Momentum, the learning rate is changed during the training cycle to adapt to the convergence rate which is happening. So remember, if you have too big a learning rate, you end up potentially bouncing around the local minimum, or missing it completely, and your loss will go massive, small, massive, small, massive, small, which means your learning rate's too big. If you see that your learning rate, or if you notice that the convergence is taking a very long time, you might have a too small learning rate. So it all depends. But I would say there's no real fixed value. Most people start on a default value. If you look at most APIs or most documentation, I think most default learning rates are 0.001 or around there. Okay, so let me go back, just make sure I haven't missed anything.
Yeah, I just copy paste a couple of questions at the very beginning to the bottom. You can just
is classification same as labeling? So so classification is the ability to in the most simplest term, predict or identify which. So if you have a data point and those data points relate to a dog, and another set of data points that relate to a cat. The dog and the cat are the labels, and the classification is the technique to identify whether it's the dog or the cat. So labeling is the label of the data, whether it be dog or cat or some arbitrary value of a label A, B, or C. That labeling happens either manually by a human or by some other mechanism, automated mechanism technique to generate those labels. And then classification is the task or the technique of identifying which label it is based on some input data. Is SageMaker similar to SAS or SPSS? Not really. SageMaker is a fully managed environment where you can do data science kind of experiments using notebooks or using something like SageMaker Studio. If you're familiar with Python, you'd be able to start coding in that environment. But I wouldn't say it's similar to SPSS. I mean, well, SPSS you can do modeling in using the specific syntax of SPSS. It's not the same as SageMaker. Does AWS ML support Markov chain? Good question. Markov chain modeling, no. Hidden Markov chain stuff, you would have to implement your own solution as well as any of the other models you mentioned. I believe there are some notebooks out there where people have been looking at DBNs, but deep belief networks, but there's no pre-built algorithm available for that one. Is there a name for issues doing with variable illumination? What's this one? So, day-night vision. So now that's a good question. So the question actually asks around, can you build models effectively where looking at day vision and night vision variations? So this comes down to around defining your problem and defining your domain. So when you are dealing with complex scenarios like day or night vision, first you want to start to build let's effectively say daisy chain different models to be able to do different types of tasks. Remember, when we build machine learning models, whether it's deep neural networks or simple linear regression models or logistic regression, we are trying to build a model to achieve a specific task. So say we're trying to do object detection in day and night vision images. What we have there is a series of different problems that we first need to solve. Number one is, can we detect whether the image is a day or a night vision image? So we probably would build a classifier which does, hey, is this a night vision image, or is this just a standard day vision image, just an image? How you would do that? Well, most likely if it's a night vision, all of the pixel shades would be of a certain color. So you would very quickly could do build a classifier which has labels that says day vision, night vision, and you could determine that. And then you would daisy chain on top of that object detection models for those specific subsets of images. You never try and do too many tasks within one model, because then you start to try and generalize too broadly in terms of the type of task you're trying to do, and it wouldn't be achievable. So yes, it can be done. You just need to break things down. How do you productionize? I'm just going to take a little bit more of a, how do you productionize deep learning models in SageMaker? There is, depending on what do you mean by productionize. So I think there's different layers of abstraction or meanings when you come to talk about productionization. One thing could be about deployment, which would be the idea of just deploying the model, which can be used as for inferencing. And then there's another whole world of discussion around CI/CD and ML ops about productionization when it comes to how do you build the necessary kind of processes in place to when you build your production environment. So productionization in a technical sense can be done from using a deploy method within SageMaker, which is effectively one line of code, which says something like model.deploy, and you tell it how many instances you want it to run across. But then you've also got to think about the operationalization of your production environment. Is like, how do you manage testing? How do you do A/B testing on your model? How do you detect data drift? how do you then retune the models? What is your cadence of retuning based on that data drift? So it gets a little bit more complicated than that one. I'm going to take 2 more questions because I see we're half an hour over, but let me have a look. Yeah. Let me have a look between moving images. Let's have a look. SPSS. Okay, what's the best way to detect difference between moving images and how to apply Cayman filters in AWS ML? So, okay. So when you say moving image, I'm assuming you mean a video. So we can apply different types of architectures, and I'll send those slides over so you guys can see, but there are specific types of CNN architectures in recent years have come out, like YOLO or single shot multi-box detectors, SSD, which allows you to run this on images. Now, I'm not sure what you mean by Cayman filters on AWS ML. Maybe you can ping me an email and I can, let me just give you my email and we can talk about this a little bit later. There we are. And one more question. Thank you for staying up till 4 a.m. in Istanbul. Very much appreciate that.
That's
more
great.
of a response. That's great. And one last one. Let me just do this for you guys. There was one question. Were there any further? Oh, no, that's for you guys. So I think that one's for you, Bill, asking about Word2Vec seminars.
Right, yeah.
Yeah, I think I've answered pretty much all of them.
Okay, great. Well, again, thanks a lot for everyone. You know, we are 30 minutes over the time, but we still have more than, about 100 people on the online. So it's great sessions. Thanks a lot, Remy, for the great presentations.
No problem. I appreciate it. And thank you, everyone, for staying up so late and taking the time. I know it's not been easy. Everyone's being at home and then forcing you another hour on a call. It's probably not the most exciting thing, but hopefully you've taken something from this. I'll send you, Bill, the slide so you can disseminate that to your mailing list. Okay, yeah, no problem. Again, thanks a lot. Thanks everyone joining us today, and I hope you have great learning. And if you miss these sessions, we have another one. And today we have a lot of topics on the AWS technologies. On Friday we have another sessions on AWS technologies. So if you haven't signed up yet, feel free to go